My name is Ian Villa. I'm the COO and co-founder of Whisper Aero, and we are building cleaner, quieter, more efficient propulsion for the next generation of drones, aircraft, and really anything that moves air.
Most engines are very loud. For now, I mean, why don't you tell us, like, just super high level, what are the things that can keep an engine like yours both efficient but also quiet?
Yeah, so the trick that we do is we take all of the sources of noise, we minimize them, and then we push the tones that you would typically hear, which is the blade passage frequency, up into the ultrasonic. Blade passage frequency, it's a function of the rotations per second and the number of blades that you have. You know, most fans, open rotors, propellers, ducted fans, they have 2, 5, maybe 20 blades. And they're spinning at like a reasonable RPM or rotation per second that puts that frequency right in human hearing. So to get it into the ultrasonic, it has to spin faster. But there's problems with taking the same fan and spinning faster. There's contributions to the noise that go with the fifth power of the tip speed. And if you imagine that, you know, tip speed is a huge contributor and it's a function of your rotations per second. You can't just spin faster to get to lower noise. So our trick has been we've developed this high blade count fan that you can actually rotate at a reasonable rotation per second that still puts the blade passage frequency up into the ultrasonic and allows us to do really clean and efficient work as it spins.
Awesome. So you're trading speed for blade count, basically.
That's
like
right.
The more blades you have, they all have to be smaller. I'm sure it's harder to manufacture. It's harder to make operate as part of a system because they're floppy and thin. But if you can do it, then you get the benefits of higher frequency sound while still being efficient and actually being a good fan and not breaking and all the things. Okay.
And high frequency noise attenuates quickly through the atmosphere. So it's actually, you know, it's better to have that high frequency noise if you can do it. But the tricky thing is, again, like, you know, our ears are quite sensitive, and you know, if you don't push it high enough, it then becomes really grating. You know, it's really piercing,
right,
really bad.
There's a thin margin of error. If you've created a very high pitched noise that's not quite high enough, then that's actually very bad.
It's super annoying, and so that's really the trick. And going to this really high blade count, extremely high blade count, theoretically sounds super easy. In practice, it's actually quite hard. There's a reason why nobody's done it before. And so there's, like you said, manufacturing challenges. There's really tough design challenges going into that. Things we had to use, you know, state-of-the-art computational tools to actually go figure out. And then this huge balancing act in order to actually get all those blades to spin and not deform while you're, you know, performing work.
Yeah, I'm excited to talk about all that. We're going to get to all that in great detail. I think maybe the simplest place to start is just, well, first of all, let's say, what are we using these for? I mean, there's so many things that you could use this type of thing for, but where are you starting and where is it going?
Yeah, I mean, we harness the power of air every day. We're starting with drones, and we're starting with work for the DoD. They understand what the value of quiet is. And so it made sense to us to just start there. And they've really been really great partners to us to actually validate and verify that our fans are indeed quieter and more efficient than other things out there. But the cool thing is our second product is actually licensing out the tech to an outdoor power equipment company to make the quietest, most efficient leaf blowers on Earth. And the play there, you know, one, we get to just make our daily lives better for everybody. But two is we've actually innovated this manufacturing technique to make the fans smaller and, you know, still at a price point that consumers can actually pay for. And so when you do that, now you have this fan that's very high performance, very low noise, and also very cheap. And when we think about attritable or expendable drones, this is now a huge enabler that, you know, higher speeds, but also really quiet, more survivable, and right at the price point that actually makes a difference for the DoD.
Totally. It's funny that the same technology used in drones and airplanes and is also in leaf blowers, but you got to move air.
That's the name of the game.
Yeah, we were just outside the studio moving some air, and maybe we can show a video, or maybe we can at least
show videos. Yeah.
Hell yeah! So then the people can see somewhere on the screen now that this thing is like actually moving air. It's not that it's just like, you know, being a little weak leaf blower. It's like actually moving. It's very quiet. My sleeping baby came up to us as we were doing. My wife brought her baby over, and he's just fine. He's chilling. He's not
That's
bothered by
actually
the sound.
the first time I've ever seen a baby in front of a leaf blower not like make a face or cry or
Baby
anything.
friendly leaf blower. That's
Yeah. I mean, we've literally had dogs at our tests fall asleep, and this is the middle of the night, like 3 a.m. Rural Tennessee.
I was wondering about that for the high frequency thing, because it's like when like other animals can hear much higher frequencies than us, so it's like you got to be a little careful. You're not going to the like dog annoying frequency.
That's right. So we tune it just we're very particular about the way that we tune it. And I recently just bought a book to look at how do different wildlife, how are they affected by these different tones?
Yeah.
We've done it in such a way that doesn't actually annoy dogs or cats or even birds. So it's really exciting. I mean, you have to be responsible about that, right? Like you don't get to an end product if it's great for us and not good to everybody else or every other animal.
Totally. The most extreme version of that would be one that kids would be very annoyed by, but adults can't hear because our hearing is degraded so far. But,
That's right.
Yeah, you got to go much further.
I mean, that book even covers like fish, like marine life. So
all right. A fish-friendly leaf blower.
That would, who knows?
I love it. Okay, let's go back to the very, very beginning, like the very basics of like what is noise, and what are the things that both cause it, or like what is it physically happening in the world, like super, super basics, and then we'll build our way up from there.
Sure. I mean, noise in our daily lives, it's created through all these pressure deltas that's happening through the air, and the air is just a medium to transfer that energy to us. I think, when we're born, we are able to hear from like 20 hertz to 20,000 hertz. Mm-hmm. And like you said, like over time, we hear a bunch of things. We go to concerts, our hearing degrades. But all around us, these pressure waves are still happening. And so when we've taken that understanding of noise and how we perceive noise, it's all been a matter of like, okay, noise is energy. Very simplistic kind of thinking there. But noise is energy. If we can actually reduce the noise and perform work in a way that doesn't create that noise, then we're doing more with the energy we're putting into the system, which is to say we're more efficient.
Yeah. I mean, the interesting thing about it though is that, I mean, because noise is pressure, because pressure is presumably proportional to like the amount of energy that's being put into the system from a fan or something. Mm-hmm. If you have something that is quieter, sort of by definition, it's like, okay, there's less energy there. But I guess the answer is we can either put it where people can't hear it.
You're using the energy to do work.
Sure. So the most efficient use of that energy.
Right.
Okay.
That's right.
Yeah. And then so if you have high efficiency, if you have, high frequency, that's what keeps something from being annoyingly loud.
Not necessarily, but because of what we do, we're minimizing that and then pushing it into a realm. So like that blade passage frequency, right? It doesn't fully disappear.
Sure, there's still pressure that is happening. Yeah.
Right. But it's there where you don't perceive it, where dogs aren't annoyed by it, and it's still minimized in such a way where we're still doing the most with what we're putting into the system.
Totally. I think there are a bunch of physical analogs that people are probably familiar with that would give them intuition about this. I mean, it's everything from like, when something is whirring up, you can hear it like start low and it like rises in pitch as it's going.
Exactly.
I mean, pitches are literally like higher frequencies.
It's frequencies.
Yeah, it's literally just like if you're singing a note. I don't know if people generally know this, but like on a piano, the same notes are just like the multiples of each other. So like a C and a C is just twice the frequency of that thing.
Right.
And so as you go up the piano, you have higher and higher frequency noise, and then eventually you go so far off the piano that you can't hear it anymore. And that's where you guys are trying to operate.
Exactly. And maybe going another layer deeper, it's not just about that single frequency, but every frequency or every tone you create often has harmonics.
Yes.
So those harmonics, we also have to think about those harmonics when we're designing these fans, and even that plays a role. Like, can you push all of that content much higher so it attenuates faster and it's less annoying?
To go into that level of detail, is it like you are? So first of all, I imagine you have to like really characterize like what all those waves are and like what the harmonics of the thing are and things like that. And are you trying to like spread across lots of frequencies, or you're trying to get it so that all of the frequencies are quiet, or like, can you just say a little bit more about that next layer of detail?
I think the easiest way to think about it is you know where the sources of noise are coming from. And like I said, you're trying to minimize those. And then where you have play to actually affect the region or frequency of those tones, you do that. And so oftentimes the blade passage frequency is one thing you can play with, but the other rotating component in there is the motor. So there's
Yeah.
motor-borne noise. So, stator, tooth count, how many poles you've got, like all of that actually plays into the motor noise, which is similar to the blade passage frequency, something that you can visually see ramp up as you go up in RPM. So all of these things, you can play around with those tones, you can minimize them. Often minimizing them means, can you use like more laminar flow over your blades? Can you ensure that there's less separation? Going back to those pressure deltas, if you can minimize the amount of pressure deltas that aren't performing useful work, then you therefore are decreasing those aerodynamic tones. And then there's particular tones that stand out, but there's also broadband.
Which is just sort of everything, like just all of it.
It's like that white noise, it's there and it's kind of like constant and maybe spread across a bunch of these frequencies. But there's ways to also minimize that, and it again goes back to like, how can I make the aerodynamics of this much cleaner?
Interesting. Yeah, I mean, there's like I'm like a rocket person, right? Like I'm a space person. So like my sort of concept of aerodynamics, we don't have to worry about noise. There's just there's nothing for it to, nobody can hear you scream in space.
Everybody's
like
far away too.
Exactly. And everything's so far away. But like for planes, which I've been starting to learn more about, I mean, a lot of those concepts are things that are obviously very relevant to a plane's like engine.
Right.
And I've done more sort of like supersonic, hypersonic stuff and like thinking about like transonic regime and things. And one thing that I know, which I'm curious to ask you about, is like when a plane, like just a normal like passenger plane is getting up, or maybe even just like a fighter jet or something, is getting close to the speed of sound, but not quite there. There are already parts of the plane that are moving. They're supersonic, which are mostly the like very tip edge, or the furthest edge out of the blades that are spinning in the engine. And so are there, like, how does, are you anywhere close to that? Like,
No.
you're
Absolutely
so
not.
much further. Okay.
And this goes back to tip speed, right?
Yeah.
So we want our tip speeds to be low. You look at like these new electric vertical takeoff and landing aircraft that are starting to be developed. The quieter ones have tip speeds closer to 400 feet per second.
Oh, okay. Wow.
And 400 feet per second, you're not even close to Mach. You're like, I don't know, 0.4, 0.3, like much lower.
Okay.
We go even lower than that.
Okay, cool. Yeah. Fascinating. So but it's still in the way that you can, is the relationship a direct trade-off between number of blades and frequent and like the speed? Are you is it a direct relationship, or do you get like, diminishing returns to having more blades?
No, there's direct relationships.
Okay.
It's the things that you're trading though isn't necessarily the acoustics. It's like, let's say you went to 100 blades.
Yeah.
That's really tough structurally to keep all of those blades in place. And so that's been part of the core tech that we've developed to enable having all of those blades. In fact, the trick is we take those blades and we put them in tension, like the spokes of a bicycle wheel. And when things get stronger when you put them in tension. And so by nature of having, 50, 60, 70, maybe even 100 blades in tension, now you can keep the rigidity of that blade. You can maintain its shape as you're actually moving at faster and faster speeds. And by nature of maintaining its shape, now when you're performing work, it's not flapping around. It's staying in place and it's doing exactly what you want it to.
Totally.
There's also, if you go back to your first propulsion course and you think about, how do I generate thrust, right? Thrust is m dot delta V. But there's this idea of like an actuator disc. Mm-hmm. You imagine like a 5-bladed fan.
Yeah.
Okay, that 5-bladed fan, yes, it's doing work along each of those blades. But if we were going to simplify the problem, like very beginner physics course, you just have a disc that that blade rotates around. And it's, before the disc and then afterwards, there's an instantaneous pressure pulse. Mm-hmm. And so if you think about it, okay, I've got a disc, I have 5 blades, and then you go to like 100 blades. Well, that 100 blades starts to get closer and closer to that theoretical optimum. In fact, if you went to infinite blades, now you're at an actuator disc.
Interesting.
And so we get as close as like physically possible to getting to that actuator disc.
That makes a lot of sense. I mean, okay, let's take a tiny step back and say like, okay, what are the core differences of your fan versus just like or your engine versus a normal one? I mean, here's my attempt. You tell me how right or wrong this is. So first of all, electric.
Yes.
I think that's important to note. Like we're not revving up the leaf blower beforehand. We're just plugging it in or having a battery.
Right.
Lots of blades, increased high blade count. That also helps both efficiency and on the noise side. It's ducted, So it's not freely spinning blades out in space like you're seeing for a lot of the, whatever, like a helicopter or something. It's surrounded by a duct.
Yep.
The what you just mentioned, the blades are tension held across that duct, and we'll talk about why that's important in just a second.
Sure.
High RPM. Even though, so this is one of the things I wrote down, but now I don't think that's true anymore. It is high RPM.
High enough RPM.
Okay.
So motors want to. This is another trick. Motors want to operate at high RPM, like up 10,000 RPM, 20,000 RPM, but you want tip speed to be low.
Right.
So it's like RPM high, tip speed low. The only way you do that is by shrinking the fan, right? R omega.
There you go. Okay. And that was my last thing on the list, which is that they stay small, that they're small diameter. So instead of having massive fans that are, we're having a bunch of smaller fans. Those are all the things I could find publicly online. I'm sure there are more. I'm sure there are secrets. But yeah, there was one particular article that really dug really deep into the engineering side. Did you guys participate in that, or was that just
I bet you it was Alon's. Was it the air current?
Yes, that one.
Oh, she's great.
Yeah,
she's
okay,
a great
nice.
reporter. Yeah.
Sweet. No, that was the most helpful piece of research for sure. Yeah, I love that article.
I think she does a better job at explaining it than we do. I think. So
yes, that is a good job. I love it. Okay, so let's talk about sort of each of those in turn and talk about first quiet and then efficiency, like how those different parts of the design would lead to something be more quiet or more loud, or having it be more efficient or less efficient.
Sure.
So electric versus gas, what are all electric engines just quieter because they're not exploding basically, or
yeah, you're removing that combustion section, which accounts for a huge portion of the noise. And we can all sort of think of this when you compare like a Tesla versus an internal combustion engine car. It's a no-brainer. The nature of like firing something up leads to more noise. So by nature of removing that and having an electric motor, okay, that already takes out 50% of the noise. But having a electric motor on an open propeller, you still have the remaining pieces of noise which are aero borne, and that's sort of where our tech comes in. That, and even if you take just an off the shelf electric motor, yes, it may have sufficient torque and sufficient power, but as we've started to optimize the Aero, we've actually found in some cases our fans are generating less noise aero wise than the electric motors.
Wow, crazy.
And so we've had to optimize the electric motors because that's the thing that gives it away.
Wow, that's hilarious actually. Yeah. It's like like when a Tesla pulls away from you, you hear the little whir, like
that's
that.
Right.
That is enough. Wow. Yeah. That's kind of remarkable.
You can just hear it. It's like broadband plus that, and then the other content is imperceptible.
Wow. Crazy. And I'm sure that probably like a normal combustion engine wasn't even part of the design space when you guys were starting off. You're like, we know we're going to do electric because it's just quieter.
Yeah. So here's the other cool thing. When you have these electric motors, the cool thing about electric is it allows us to decouple the components in your powertrain. Like back in the day, think about turbojets, turbofans, power is coupled with thrust, right? They're on the same shaft. You have to burn fuel in order to rotate the fan. Right. The rotating the fan creates thrust. Well, now that you're electric, all you have to do is pull electrons into that electric motor to spin the fan. Those electrons, though, like the actual power and energy source, that can come from any number of things: batteries, turbo generators, sucking up fuel, converting that to electricity, passing that into a high voltage bus, a fuel cell. So just by nature of that, I think for us, we care a lot about thrust. And then it goes back to like, what is the mission you're trying to solve? If your mission is like a 1,000-mile flight, maybe you still have a turbo generator, and that turbo generator is shielded. It's not making as much noise as it would. It's also not trying to do like the thrust part of the work.
Yeah, right.
So it's doing what it needs to do to generate power and energy, and then it passes that out to our thrusters.
Right.
But yeah, that's kind of like the very nuanced answer there.
No, that's and I'm sure there you could have an aircraft with different modes too, where it's like we have the super silent mode, but then we also have just like get there fast mode, like for vast majority of the transport, something like that.
I mean, there's cars today that shut off its engine when you're braked or stopped at a light. It's kind of like that.
Yeah. Regenerative plane.
Maybe. But yeah, there's modes where, you could, and we think this actually matters a lot for regional air mobility, where you have a lot of your energy and reserves energy, reserves power stored in that turbo generator plus fuel. But for the vast majority of your flights, you're actually flying electric on a battery.
Oh, cool.
And so, the turbo generator is there for safety, but also for extended range. But otherwise, you could fly all electric and you're getting all the costs and efficiency and, sustainability benefits by flying that way.
Nice. Very cool. Okay. So we talked about electric. We did also sort of talk about why lots of blades makes it so that it's quieter, but
Sure.
can you just summarize quickly? It's because of the blade tip speed versus,
So you have lower blade tip speed. You
Yes.
have more blades doing useful work. You now have like a very benign pressure pulse coming off of those blades. And also because the blades are smaller and the cords are smaller, we can achieve much more laminar flow over the
Yeah.
top and lower surfaces of that blade. And then the other thing to think about is there's portions of the noise related to how much of the air you displace. It's like thickness noise.
Sure.
Well, if you think about an airfoil,
yeah.
and you think about shrinking that airfoil down, you don't just like shorten the cord and it stays fat. The
Right.
cord and the thickness scales together. And so, imagine I had like 20 blades and then I went to like 100 blades, same diameter. You could actually
So they're
save
each, okay.
you could save like 20x of the volume.
Sure. Yeah.
Like,
yeah.
So by nature of doing that, you've now reduced that thickness noise component.
Interesting. Okay, cool. So, just to this tends to be like a more like beginner podcast or whatever.
We're
you
just
know,
going
like
in.
people who don't know, but I love it. It's perfect. So just to like say the terms, like what you were saying was more laminar flow, which basically means that the flow is sticking to the wing better and not
It's staying attached.
and not like breaking apart in a way that makes it turbulent and crazy and
That's right.
swirling. That's actually we didn't actually talk about that. Maybe let's go to ducted, and so we can talk about this directly.
Let's go to ducted.
A lot of those swirls that come from a normal blade happen at the end of the wing. Like they're kind of falling off of the end and they do these crazy spirals kind of off the end of the wing. But because your fit blade is ducted, because your blades are ducted, you don't actually have to worry about that,
Yeah, to
right?
be more precise, because our blades actually have a tip and there's really a shroud around all of those blades.
Yeah.
That vortex loss, you don't get a shed vortex off the tip. And another way to think about this is every single blade has its own wingtip.
Right.
And so rather than losing energy from that shed vortex, we actually are able to keep it attached, and that saves you about 7% in efficiency.
Interesting. Is that a function of the duct, or is that a function of it being attached along the edge?
It's really a function of the tip having a shroud.
Okay.
If you go to like a turbofan, next
Yeah.
time you fly, look at the blades. There's a very fine
There's a tiny gap in between. Yeah, exactly.
That tip gap actually leads to a lot of losses. And the way that traditional turbofan manufacturers get around this is they just have a really big fan, and so that like materially that's a very small
Sure.
proportion of the overall fan. Now, if you were to take that then and scale it down, just imagine you could scale down a turbofan to something that's like the size of your coffee cup. Well, manufacturing tolerances don't change.
Totally.
Maybe they change a little bit, but like that gap is a larger proportion of that overall fan. That means that same fan design at this size, maybe that fan's like 70% efficient or worse.
Yeah.
We can still keep like 92% efficient fans, no matter if you're 4 inches or like 4 feet.
Yeah. But then the other harder part too is that when you're adding the more blades in to that, each blade is thinner, and then like I'm sure there's much more wiggle in terms of like getting that tolerance to be perfect for a very like loose blade or whatever. Like what would you even call that? Like what would you call the like looseness of the blade?
There's like aeroelasticity that happens when it's flying, and if it wasn't supported,
right?
So rather than having a blade that's just cantilevered, we can actually support them at both ends.
Yeah,
and this is where actually going to a higher blade count helps you, because now when you have multiple blades, it's not like I have a blade here and then I have a blade here and then I have this like really big shroud that has to stay between them.
Yeah,
and now you've got like this T shape that's got to like all wiggle together.
Yeah,
no, you have a bunch of these blades that are all supporting each other.
Yeah.
And, connected, you have this now continuous shroud, but also you have, going back to that actuator disc idea, you have a bunch of blades that gets to larger solidity, that gets closer to that theoretical, optimum.
Totally. I think so I get the obvious question then is like, why wouldn't large engines do this? Like, why don't we have all the 7, the passenger
because
jets?
They spin fast.
Yes.
They spin fast.
And they would explode. They're like because if you had the big rotating, what do you call that part?
The shroud.
The shroud. If you had the big rotating shroud on a large engine,
a lot of mass.
It's a lot of mass. It's also like because it's going fast. Would it literally just like like explode outwards or whatever? Like, would it be able to support itself?
I think there might be ways to design it, but it gets a lot trickier, right? And especially if you're trying to go at these higher speeds with much larger fans, it's not just about the mass of it; it's about its inertia. And you now have this, mass at the end of a very long blade that's now rotating and getting closer to sonic speeds. Like,
totally.
Yeah, you're making a tougher problem for yourself.
Interesting, crazy. Okay, so we talked about electric. We talked about lots of blades. Do you want to talk a little bit more about the duct of like what's the value of a duct and like why does it help with efficiency? Why does it help with noise? Well, for now, let's talk about why it helps with noise. But
I'm going to couple the duct and the stators.
Sure.
So if you imagine a propeller. If you could visualize the flow, the flow isn't just going straight through the propeller like a straight tube.
Sure.
It's actually sucking in a bunch of air, and then as it passes through, it compresses, or compresses maybe not the right word, but it actually filters down.
It's coming through and being pulled into the engine.
Right. And so, and then on top of that, when it's getting pulled through, it's introducing a lot of swirl, right? These propellers are rotating. That swirl, similar to turbulence, that swirl is losses. So the cool thing about a duct is the duct allows you to really control the flow through that fan. And then we add stators that deswirl that flow. And by nature of deswirling that flow, we now get more useful work. Rather than having, if you imagine just imagine air had like vectors to it.
Yeah.
Rather than having a bunch of vectors that are turned and
Sure.
slightly swirling, we're now using the stator to straighten them back out and have all of these, portions of the thrust pointed
directly where you want it to go. Yeah,
exactly.
you don't because you would lose to the angle in between them. But instead, it's going straight out the back.
And like even the shaping of the duct allows you to coerce the flow to move the way that you'd like it, especially, if you're trying to design the fan, for multiple speed regimes, you really you want to have that tailoring. And also, with a propeller, the flow contracts as it will, right? It's just kind of like it's getting sucked through, and then you have this ambient, and then how it contracts is like what the air will do. Whereas the duct, you can actually shape the duct to contract the flow the way that you want, or expand the flow the way that you want. And so then when you've got this duct that's shaped in a particular way, and you've got methods to control your area, the exhaust area, there's ratios between your exhaust area and your fan area that actually allows you to have optimality across multiple speeds. So then the other cool thing about ducts is ducted fans allow you to go to higher speeds.
Yeah.
Not surprising, right? 737 ducted.
Right.
787
open
ducted.
propellers on it. Yeah. You don't have prop planes anymore.
No. It's an enabler of higher speed. And then when you think about noise, right? Let's go back to the propeller. You have this propeller spinning. There's a portion of the noise, like loading noise, that's going to come down, but there's also thickness noise that goes out, that emanates outward. And so this duct, when you've got it in place, what's happening to that thickness noise?
It's capturing it.
It's getting shielded. You have natural shielding due to the duct. And so if you think about the way that the noise is going to emanate, rather than having a point source that's going to spherically emanate and just kind of like hit everything, you have a duct that can kind of concentrate where that noise is going to go and ensure that, in certain directions, you actually are not going to annoy people.
So I think that the next place that we should talk about, I mean, a lot of these things sound heavy, honestly. It's like, okay, we're adding a duct. That's weight.
Sure.
We're adding the stator. That's weight. We're adding I keep forgetting what this part is called. The shroud. We're adding the shroud. That's weight. So all of those things make it harder to lift something, and that makes the ratio of the weight of the thing to the actual thrust that it's providing lower. So what is higher? What is the way around that? Like, how do we get what do we get in terms of efficiency? What do we get in terms of performance that allows us to offset that additional weight?
Sure. I mean, there are trades between the actual efficiency you've got as well as the weight you have to hold on board. So, for example, if for a more efficient fan, you would have to carry less energy, right, to go the same distance.
Yeah.
So that's the first part of like the thinking that we have by nature of pushing to this high efficiency fan. Even if we are carrying some weight and your high efficiency, you actually can overcome some of the deficiencies of batteries or some other energy sources. But the other thing that we do is, we try and find multiple ways to leverage our components. So, for example, our stators aren't just deswirling the flow. but they literally can be there to structurally, actually add structure to
Sure.
the overall fan, or they can actually be used to pull heat away from that motor. Or you can also use them to actually conduct or move electricity into the motor.
Oh, interesting.
And so as you start to find like ways to look at these synergies, those synergistic ways of like aligning or multi-purposing the elements within that fan, reduce the weight, but then also add to the overall efficiency of the system.
Interesting. I mean, this is also my question about keeping the engine small, because the downside to more smaller engines is that there's a lot of stuff that in theory you would get returns for if it was just one big thing. Like you wouldn't have to have multiple individual shrouds. You wouldn't have to have like whatever. You wouldn't have to have multiple individual ducts that are surrounding the whole thing. That piece of it seems like that is also a big weight penalty, but that seems like the answer there. It's like, okay, if there are other pieces of the system design that we get benefits from that offset those, like temperature or something. I'm sure that
Thermal is big.
Thermal is big
That's
for
where I was gonna
small.
go.
Yeah. Okay.
So, like if you imagine cube square law for a motor and you're trying to reject the heat.
Yeah.
As you go to these larger and larger motors, if you want to keep it air cooled, the surface area of that motor doesn't increase fast enough, right?
Right.
The volume of your windings, your magnets, it increases much more quickly. And so now you've got a huge heat problem, and to reject the heat, you no longer can convect it away. You actually have to add liquid cooling. Well, that's mass.
Yeah.
That's, sure, maybe you have a bunch of these small ones, but in reality, as you go larger, you have to cool that. And even if you think about like a traditional turbofan, there's a bunch of like thermal components you have to worry about there, a lot of complexity built into that. So that's why going smaller actually helps you. Within reason, for a small enough fan, now you can actually convect heat away just using the natural flow coming, getting sucked through that fan, through the stators, and then pulling heat away from that motor. And you get a little bit of a help from that rejected heat towards your thrust.
Oh, interesting.
Yeah.
That makes sense. Well, one thing that you mentioned very briefly up at the top that we haven't really talked about yet is the different types of noise and how they are, contributors to this problem that you're trying to optimize for. And I think that you've called the two broadband and tonal, where broadband is just sort of like all of it, and tonal is these like spiked things at particular frequencies.
Right.
Can you just talk more about how you think about those, and then also how these different parts of the system are, addressing them?
Yeah. I mean, again, name of the game is minimizing everything. This broadband noise is going to be spread just across a bunch of different frequencies, but it's possible to move that broadband, a collection of this kind of like incoherent, but like across multiple frequencies, noise into a higher region. And when it's in a slightly higher region, you now can either use atmospheric attenuation to your benefit, or there's things like liners you can integrate, and they've got liners on even traditional turbofans that can pull that noise away.
Interesting.
The cool thing is when you have higher frequency, like broadband content that you're trying to, get rid of, those liners actually decrease in size.
Interesting.
And when they decrease in size,
Sure,
they
makes
decrease
sense.
in weight.
Because higher frequency means that you don't have to have as thick of a thing to
Right.
absorb it, basically.
Exactly.
What are those things? What do they actually look like? Are they like blankets or like like a noise blanket kind of thing?
So you buy a Ryobi leaf. Now
Yeah.
I know like way too much about leaf blowers. You buy a Ryobi leaf blower today,
Yeah.
and they actually have a foam on insert.
Really?
Yeah. If you
Interesting.
take it apart,
Fascinating.
and that foam insert is
It's
their
the same.
liner.
It's the same concept as like a recording studio, or like we have them for us at we do like a bunch of like electromagnetic susceptibility testing or whatever, like
Yeah.
EMI EMC testing.
Sure.
And for that we have the cool like polystyrene on the walls
Yes.
that like absorbs the right frequencies.
Yeah.
Fascinating. It's just that.
Kind of. There's
could be
different.
just
There's
that.
different kinds of liners you could do, and there's like more advanced structure ones where now it's not necessarily a foam, but there's like interesting structures you can use. Yeah,
Very
and
cool.
you can like layer them and tailor them to particular frequencies
yeah,
you
sure.
really want to isolate.
Interesting.
The tones themselves, again, you want to minimize them and then push them to regions that your ear can't hear.
Sure.
But you can't do that with every single frequency.
Yeah.
So, for example, motors, like as you're spinning up a motor, even some of these best motors, their natural tones will still be in like the 1,000 to like 5,000 hertz range. You can do things to kind of like isolate where they go, but the name of the game is minimizing. So even if they're as least intrusive as possible.
Yeah.
Yeah, and then the last part of this is just like, how is this fan going to be operated? And so if we think about how we perceive noise, there's tones that are just kind of like drawn out, inconsistent. That is perceived or thought of as very different than something that's like very impulsive.
Sure.
It's like, just think about like a very like sharp shrieking noise as opposed to just like a hum from
like, you mean like
fan.
the ramp up to the noise, basically, instead of it being like a spike, it's like a slow increase.
Sure. Yeah. It's like impulse. The idea of impulse, force times time as really short time, boom. Like that might be like very piercing and like, it sucks. But then, it goes away. You're fine. Versus, you're sitting in this room and you've got a fan on and it's like loud the entire time. That, it may not affect you right up front, but over time that droning may actually kind of like, bring it back to leaf blowers, our homes, each home, the walls of your home, it's got insulation inside. That insulation helps to, get rid of the noise that would be in the outside. But, when you're in a Zoom call and you hear somebody's leaf blower, that leaf blower has a very low frequency blade passage frequency, but also low frequency broadband. So if you can move that blade passage frequency up into the ultrasonic and then also have this higher frequency noise, higher frequency broadband, it gets eaten up by the insulation within your home. And then now we never have to worry about hearing leaf blowers and waking up in the Saturday.
No, your neighbor is now no longer annoying. You can actually be friends with them. Yeah.
Yeah. Not that. And if you're working from home, like you can take a Zoom call and never have to worry again.
Yeah, that literally happens. We were talking about that before. It's like whenever there's somebody working outside, you can just hear it right through the walls.
We were literally pitching an investor once, and we were talking about the leaf blower, and then like on cue, leaf blower landscaping crew started coming in. It's like,
you should just do that. You should, like, whenever you have an investor and they're working from home, you just like hire a lawn crew to just like, hey neighbor, can we offer you this nice service to like clean your lawn at this particular time?
Yeah. I think we have we'll help build the leaf blowers that neighborhoods will actually love. So.
I love it. Okay, let's talk about efficiency. So all of these things, like the simplest way to like make it something not noisy would just be to like run it at a super low speed and just like not get as much performance out of it. But you have to have high performance for drones. You have to have your leaf blower actually move air. So I'm curious, like at the very high level, like are there particular like benchmarks that you're trying to hit from the efficiency side that would make it like good enough or something? Or like how do you think about it from like okay, we could trade off and just get less performance, but like how low is too low for performance? Like what are you trying to hit for that?
Yeah, I mean, there's different ways to think about it. The first that I already mentioned is the fan efficiency. So the fan efficiency itself, like we've maximized that. Mm-hmm. The second thing to think about is like, okay, once you integrate the entire fan or electric ducted fan, and now you're putting it onto a platform, an aircraft, a product, how many pounds of thrust are you getting per watt going in? Mm-hmm. That's also a pretty important metric. And then what's the relative delta of that versus, the competing product?
Sure.
For the leaf blower, what we've been able to show is like we can not only move 40% more air, but we can also use 40% less power and still be 45 dB.
Wow.
At 50 feet.
Damn.
Yeah. So all of these kind of combinatorial metrics, like efficiency matters, but efficiency only matters if you're still getting the end result, which is moving air or propelling something through the sky and still being quiet. And that kind of like multivariable objective, we're balancing that all the time. And there's going to be cases where you sell out for efficiency and it's maybe, not moving a lot of, or maybe it's moving lots of air. Maybe it's on a drone. And by nature of selling out for efficiency, you can go with like a more like a heavier motor. That's like one trade you could do. Or maybe you just want to go for like a COTS motor. The COTS motor's got like 70% efficiency at the shaft. It's like, okay, great. Then I got to make sure that my fan is very, very efficient. And then I got to make sure the integration of that fan doesn't have any more losses to overcome the lossiness of that electric motor. So the actual efficiency stacking matters a whole lot.
Yeah, this is because you ran that test, right? Like I think this is on your website publicly. Is like the test of your. It was your fan with a COTS motor. Was that what it was?
There were two. So there's multiple tests.
Okay,
we're big believers in showing and not just telling. So there's the first video where we have our 10-pound thruster against 2 electric ducted fans that you could buy off the shelf, and then 2 aeronaut cam carbons. These are open props. That very clearly shows like not only the noise delta, but also an efficiency delta. When you integrate that onto a drone, we actually see, 2 times benefit over the other electric ducted fans. And I think it's almost like a 7x delta over an open prop solution. So what does that tell you? I mean, that means that you not only have to optimize the efficiency of that ducted fan, but also the integration matters a whole lot too. If you take a really great electric ducted fan and you integrate it in a sloppy way, you're going to introduce losses. Like, if you put a fan and it's ingesting really bad air, it's going to lose a lot of that efficiency. Versus if you take a bad fan, but you integrate it really well, now maybe you get a little bit more performance out of that. But really what you really want is high efficiency, high performance fan integrated in the right way so that now you're yielding all of the benefits and it's not, just additive, but actually multiplicative in terms of the performance benefit.
Totally. I think this is a fine time to turn to sort of like the what makes this hard section, because I think the conceptual way that you've like oriented this product, like the concept behind the product, like the physics of the product, make a ton of sense. I think the engineering is really hard. Like actually getting that concept to be in the world and working sounds really hard. And so one thing to share with the audience before we get going is that you've actually been doing a little bit of like a Manhattan Project vibe with how you've built this product, which I absolutely love. Would you mind telling us about the facility and like where all this is being built and where you're proving that you can actually turn it from physics into engineering?
Yeah, I mean, we're based in Tennessee, so we've got 3 offices now. We've got 56,000 square feet, a 40,000 square foot factory, an 8,000 square foot engineering facility in Nashville, and then another 8,000 square foot sort of flight test hangar. But we weren't always there. We actually, my co-founder, Mark, he bought this resort in rural Tennessee, and it's on a lake. It's 20 acres. There's 12,000 square feet of lab space, and then 28,000 square feet of apartments because it was a resort. They were units. And so in the middle of COVID, we raised a pretty substantial seed round, hired the starting team, and then we all literally lived, worked, played together on this resort, which was awesome.
That's so awesome.
We had the lake.
It's like dream startup vibes, honestly.
Yeah. I mean, if you really want to like live it, and you have to if you want to survive early days. That was an ideal space, especially in COVID. So we had a lake. Seriously. There's a beach. We had a garden. There's a chicken coop. We get like fresh eggs every day. Tennis courts, and the tennis courts was where we would test. Like,
nice.
we would test in the middle of the night. Mark hadn't completed all his renovations, and so some of our earliest tests, we were like hanging off the rafters of a building. Probably not like OSHA safe.
This is classic startup. Like in the very early days of Astronis, they wanted to test like a gyro that was on the satellite, and the solution was hang it off of the second floor of the loft and just like spin it on a string and then let it try to stabilize itself. Yeah. Like classic.
You have to bootstrap in like any way possible. So we started there, and that became a proving ground for us to really rapidly test the tech, ensure that we hit all of the metrics we thought we were going to hit. And it was going back to that, can we get 90% fan efficiency? Can we be really, really quiet, achieve this ultrasonic blade passage frequency? And we did that. It was just a really awesome, place to go build. It still is. Our flight test hangar is 5 minutes away from there.
Oh, nice.
The factory is 10 minutes, maybe less than 10 minutes away from there. So we're kind of building up this really interesting aerospace community in Tennessee.
Yeah.
And we're leveraging all the benefits of precision manufacturing, EV, electric mobility that's starting to move to, say, like Ford, GM, Nissan, building up factories, LG Chem. And then you have aerospace surrounding, right? So great schools like Georgia Tech, you have Huntsville, Alabama, just a lot of really surrounding areas we can pull resources in an unconventional way, but actually makes a lot of sense the more you look at it.
I love it. And so at that facility, you had to prove that this physics idea of like how you could build an engine could actually work in the real world. I'm sure that transition was hard and took a lot of learning and a lot of prototypes and a lot of testing and, ultimately figuring out, okay, here is a design that works. So like, here's a point design that we can build around, that kind of thing. What were sort of the biggest barriers between physics and engineering for you?
Yeah, I think, we have a really great design team, like, while the hardware is impressive, to get there, we invested a lot in actual like CFD,
Sure.
multi-fidelity, variable fidelity tools, and then coupling those tools so that we could actually optimize, which is easier said than done. Like a lot of people will take like an ANSYS or something off the shelf and then run those. But for what we were trying to achieve, like one, a lot of these acoustic prediction tools just don't exist. There's tools that have been built before, but oftentimes acousticians or acoustic engineers, they're dealt the aircraft design after it's kind of locked.
Sure.
Very seldom.
It's like post facto analysis after it's done. Okay, what's it going to sound like, as opposed to like iterating fast and having to do it like many times over and over and over again.
Right. Someone designs the airplane or the engine. They're like, okay, now your job is to make it quiet. And it's like, dude, you like designed the thing. I can't do anything up front. So we had to design this computational framework that could combine, high fidelity acoustics, aerodynamics, structures, combine them all into sort of the singular framework, and then be able to make those trades, right? You think about old school aerospace. You got like an Aero guy. He's like, all right, I did my part. Here you go, structures team.
Exactly.
And they just kind of like pass it down the line. What we wanted to do is actually have all of these disciplines operate at the same time. So when we run an analysis, it's not like, okay, are we getting to a closed fan? It's like, no, we have a bunch of these closed designs. Let's optimize over millions of them and get to actually what we want. So that was one of the first like really tough barriers to overcome. But then once that system was working well, and we've continued to optimize it over time, then it was like, okay, we've got designs. How do we know we could build it?
Yeah.
And so then the next thing is like, okay, we're trying to build a fan with more blades than anybody's ever proven was possible before. Who do we go to build it?
Right. Contract manufacturer, like who's going to,
We tried everything. I mean, like we went to places that would 3D print, metal 3D printing. Yeah. We tried just like regular 3D, like could we 3D print using some interesting materials? Are there plastics with carbon fiber we could play around with? Could we CNC the thing? And ultimately we found like the right combination of vendors to be able to CNC some of these parts. But it's non-trivial. It took us like 5 months after we had a design to actually identify the first shop that would even be willing to try this out for us. It was that kind of crazy of a task, because even the trailing edges, like we're talking about micron level tolerances.
Yeah.
And so it's like, okay, I just need you to build me, a first run of 100 blades. I'm like, who are you? You're like a nobody. How do I know that this is legit? Why am I going to spend R&D time to like figure out if this works? And also it's the middle of COVID.
Yeah.
My shop's, I don't know when my shop's going to shut down. Like, how do I know that you're going to even pay me?
People would be surprised how hard it is to get people to take your money when you're an early startup. It's like, I want to pay you a lot of money to do this, please. But they're like, I don't know. Like,
supply chain's tough. I mean, but that was the next big barrier. And then over time, we found more and more people willing to build what we wanted. And we also gotten sharper about designing things relative to what's, feasible manufacturing wise.
Yeah. I think it's interesting that, so the kind of like, maybe, I don't know, like more standard, but the only reason it's standard is because like SpaceX and Tesla did it, which is just bring everything in house, just do it all yourself. Like do the design, which you guys have done, or like we're doing. But then for that manufacturing, okay, now it's time to buy a CNC machine, or like now it's time to buy the crazy 3D printers or whatever it would be. Like, did you guys intend on having that as like from the very beginning? Like you wanted to be designers, you wanted to be, the people who are like using third-party partners to manufacture a lot of the parts, or is that still like, is that just like a stage thing? Like eventually someday you'll go just manufacture everything.
So I think it's helpful to think about like what do the big primes do today? Like they don't build everything in house. Like Northrop doesn't build their wing, skins, wing structure. They won't necessarily do that. They'll go do like a Spirit or some other manufacturers and then integrate it themselves. And then when you think about like early stage startup, you don't have like all the capital in the world to even bring everything in house immediately. So it's like we knew there was a world where we could actually outsource some of the things that were easy. And also we needed to focus on the parts and the pieces of the system that only we could design, but also were strategic for us to go manufacture. And so understanding that, you just have this like many-sided Venn diagram where, okay, some of these pieces we could 3D print. We should probably buy some like 3D printers to go rapid prototype, and then maybe we could use like SLA for some of these parts. But the blades themselves like were really tricky. So we were able to get like a 3-axis with an optional 4-axis CNC to go like prototype stuff. But honestly, it's still like, after playing around some more,
needs more axes.
we could use some more axes, and like maybe we aren't the ones who've had like the most experience to go build this out.
Yeah.
Let's see what we can get out in industry. And then over time, as we've scaled the company and started to build more of these fans, we can get a lot more strategic. It's like, okay, the blades matter a whole lot to us. Okay, we should probably bring more of that in-house.
Sure.
Or there's other pieces of this. The composites, okay, there's a bunch of composite vendors. We don't necessarily need that.
Yeah.
I think over time we'll bring more and more of the stack in where it makes sense. And if there's like best of players in the world to team up with, we're not opposed to teaming up with them as well. When you have this system, you can put them into drones, you can put them into larger aircraft. I think what's really interesting is that there's a whole new field of aviation to be unlocked, where we could fly every day or fly things every day with this technology. Even some of the systems that are flying now, you imagine drone delivery, still too noisy. I mean, Google Wing has had blockages in Australia just because, or bans in Australia because they've been so noisy.
Oh, really? I didn't know that.
Yeah.
Crazy.
They don't want to talk about it, right?
Yeah, fair enough.
And I think, it's not going to get better as we fly more unless you actually solve the problem itself. So as we start to get to, more drone delivery, people wanting these services, even like medical services or drones as first responders, it's really critical that we have quieter, more efficient systems flying every day. Same thing too with just transportation, right? Like the existing air transportation system is getting clogged. We need newer aircraft to fill the roles that existing aging fleets are currently flying. We should be responsible and replacing those aircraft with, more efficient, quieter systems responsible to neighborhoods. And there's a world where we're not just going to these major hubs. Like 70% of the hubs in 70 airports. 70 airports in the United States carry more than like 85% of the traffic. Yeah. We should be able to distribute more of that. And so flying 100 miles every day shouldn't be unheard of in like an electric regional jet. And so with these fans, I think not only are we replacing propulsion, but we're thinking of aircraft in new ways, right? Like distributing, rather than going to one large fan, distributing these fans on the leading edge of a wing, getting blown lift, having 8 to 10 times more lift off that wing. Whether you're cruising or whether you're taking off.
Those designs look so cool, by the way. It looks so different than anything you've seen before. Because the engine is literally inside of the wing, basically.
Yeah.
It's like, it's not a thing that hangs below a wing. It is literally the wing.
Yeah. You now have a component that you have freedom to integrate, as opposed to like, I've got this big engine and I got to stick it somewhere. It's like, no. These can go anywhere. Your powertrain is your aircraft. Like you can place these where you want them to get the most out of that. And also by nature of being electric and flying electric, you can fly more cheaply. In fact, I think there's a world where you can fly regionally, like San Jose to SF, and it would be cheaper than, driving your car. Federal reimbursable rate of driving your car today is like 65 cents per mile. We could do this with like 50 cents per mile.
Cool.
And being able to enable those kinds of flights has transformative effects on the way that we live.
It is interesting. I mean, I think you would actually really like this book, at least the first chunk of it that I read. The Flying Car one? The Flying Car one. Yeah. So there's published by Stripe Press. There's this book. It's called "Where's My Flying Car?" And the basic premise at the beginning of the book, which I found super interesting, was things just haven't changed in the past. Like since the golden age of aviation and aerospace, like we had so many designs that were out there for like these the funniest design that I saw was one that's like a normal car, but then you drive into a hangar and just like slaps wings on the top, and then that like can fly you around. Like there were so many different possible designs that were out there, and now there's just not. I mean, we have the electric like VTOL guys who are trying to revive this as well, but there's really not like remarkably different ideas about air travel now than there have been recently, like as compared to what it was back in like the 1960s or something.
Yeah.
So
I mean, batteries and electric motors and advances in manufacturing, as well as computational design, these are all allowing us the freedom to imagine a new world of aviation. And so I think, it's early days. People are starting to figure out like what is those first manifestations. But I'd like to think that our propulsion systems is that second gen, and that's going to open up the world of new opportunities that are smarter, more efficient, affordable, and accessible to many more people.
hell yeah. That's a good place, as good place as any to wrap it up. Any place you want to send the audience, people that you want, like places you want them to check out, want them to apply to join the company?
Yeah. We're hiring all the time. We're looking for sharp talent. We're in Tennessee. Cost of living is great. Great food, great music, great people. So definitely apply online.
Hell yeah, man. Thanks for doing this. This is awesome.